Today, I'm excited to share with you my research project focused on leveraging the large language model with domain adoption. The goal is to enhance the community directory through deep learning text summarization for machine readable cataloging standard description nodes, also known as MARC nodes. To begin with, let's start with a short introduction. This research project creates a system utilizing NLP to automate the process of writing summary in MARC node standard. The standards is widely used in library and information system. But in the old days, the community service directory in South Australia was a physical print with basic description. Nowadays, this directory is digitalized with richer content like the services the organization offers, the opening hours, the audience they target, even comments. Navigating this knowledge maze can be challenging. Our research motivation is to transform this experience and bring benefits to both user and the operational side of our community. On one side, we're creating a user-friendly directory to simplify research access, understand community dynamics, and provide quick insights for an enhanced user experience. These lists include diverse stakeholders who can benefit from our contributions to the community directory. Let's address the operational side. Currently, manual efforts heavily support our directory, driven by dedicated volunteers. Imagine lighting up the load and saving time and resources by automating the process. This ensures an up-to-date directory, making life easier for them and benefit the SA community. In short, our research aims for a win-win. We enhance user-friendliness for the community, streamline operation for volunteers, and embark on a journey toward a stronger, more accessible community in South Australia. Moving on, we have four key research questions to investigate. In text summarization, significant model types and techniques like transformer and BERT are used. The current problem includes a lack of ground truth and domain adaptation, which can be addressed through embedding and fine-tuning. Evaluation techniques involve measures like loss and Roche score. For test summarization, the SA community dataset from data.sa with open and closed field columns will be used. Next, let's explore datasets. Allow me to introduce the SA community database, CVCRMDB for short. It covers description data like organization bio, names, IDs, addresses, and services. One thing to notice is that the format is in OpenFill, meaning they are in unstructured text. Complementing this dataset is SubjectDB. This explores categories over 14,000 organizations. The dataset is straightforward with all the predefined indexes, so-called closed field. Both are available through SA Community website, also SA Government Data Portal. After a series of data mapping, cleansing, and preprocessing, the combination of these two datasets with open and closed field components provides us the backbones for this research. Open field data is unstructured text without specific format constraints or validations, offering flexibility to capture diverse and dynamic information. On the flip side, the closed field provides predefined structured categories, maintaining consistency and data integrity. The research design evolves around three phases: pre-processing, model development, and application. I will show each phase in detail later on. Please feel free to pause the video if you want to know more about the workflow. Moving on to the data and task. The dataset composition reveals a high ratio of unlabeled data with limited ground truth. Also, they contain domain-specific information about organizations in South Australia. The main task is to perform summarization with domain adaptation. We aim to leverage the unlabeled data by utilizing extension embeddings and fine-tuning to enhance the performance of our summarization process. Here, I will share one specific handling of data processing with organizations with multiple branches. Oftentimes, entities like Red Cross, RSL, in the directory they have same ground truth and services. However, this duplication can significantly impact the effectiveness of summarization model. A reliable solution is to use NER to recognize geographical locations and then remove them from the entity names. In the experimentation with SPACY English language small model, it identified close to 400 entities, while the large one catch 556. However, a significant portion of entities still remain unidentified. To address this issue, training a custom NER model for a city in South Australia is done. 2,000 annotated samples were used to train the model on top of the existing English small model, and the output have been promising, showing majority result on the NER type. Now, let's explore the methods we have employed. It is a twofold method. Our journey begins with Expert, short for Extended Bird Pre-trained Model, a powerful LLM. The progress began with the pre-training of BERT to transform into Expert. Once this pre-training is complete, we move on to the next phase where we fine-tune Expert for the downstream tasks for summarization. These fine-tuning steps enhance the model capacity to generate clear and content summaries. To start with, we concentrate on the pre-training of Expert, where we infuse the original BERT with domain-specific vocabularies. The approach unfolds in two components. On the left, there are extension vocabularies and embedding layer. This enables more meaningful tokenization of the input text. On the right-hand side, the graph shows how we enhance each transformer layer of the original BERT, often refers to the off-the-shell, by adding an extension module to its side. And then we use the weighted combination mechanism that allow the off-the-shell and the extension module to cooperate. This quickly shows how the extension vocabulary is built. Regarding to the embedding layer, we have word embedding of expert, which are derived by combining the original word embedding with the additional word embedding. On top of that, each layer has an extension module with the following architecture. Our methods involve vocabulary adaptation through transfer learning, with BERT based on case at our starting point. We incorporate unlabeled custom datasets into the pre-training process. The result is a freshly adopted model equipped with specialized vocabularies. In experiment 1, we investigate the impact of data representation. We compare open field columns to a combined dataset that include both open field and closed field columns. This experiment aims to investigate how the choice of data representation, open field versus combined, affects the performance and the outcome. In experiment 2, we are exploring different module size, ranging from S1 to S5. Here, S5 represents a full-size transformer module. S1 to S4, on the other hand, are partial module, each with a unit ratio compared to a full-size module. The table here presents insight into the corresponding hidden size, the number of feed-forward layers, the intermediate size, and how these parameters refer to the original BERT model. The experience helps us to understand the impact of module size on our model performance and capabilities. In the case of Expert, it employs a dual configuration setup of vocabulary list and architecture. We pre-train the model by initializing it with predefined weights. It is important to notice that the off-the-shelf part remains completely fixed throughout the process. However, we make updates to the extension module and the weighting board during the training phase. The table shows different hyperparameter setups for the experiment 1 and 2. When we examine the pre-training foundation loss, the best outcome are achieved with open field copies with the following batch size, learning rates, and epoch. We will proceed this set of modules to the downstream task, focusing on task summarization. Now moving on to expert sum. To convert expert to expert sum, it involves a critical adjustment to the segment embedding architecture. This adaptation is essential to ensure that expert sum can effectively generate sentence representation. To distinguish multiple sentences, we utilize Stanford Core NLP to enhance the model's comprehension of sentence structure. Building upon the foundation of expert sum incorporate additional components for positional embeddings. These embeddings are initially set randomly and fine-tuned alongside other encoded parameters, as demonstrated here. Experiment 3 compares expert with different embeddings, S1 to S5. with the baseline summarization model without extension embeddings. We will use a specific dataset with ground truth, and the experiment will show impact of extension embeddings on our XBERT model performance in Roche score compared to the baseline BERT model. We're working with approximately 600 pairs of article and their corresponding ground truth summaries. To prepare this data, our initial steps include tokenization and sentence splitting. Here are the hyperparameters set up for the experiment. When it comes to fine-tuning, it's important to highlight that we have achieved the best result with the fine-tuning loss configuration labeled as S2. This particular setup has proven to be the most effective in optimizing our model's performance. In terms of performance evaluation, using Roche F1, F2, and L score, we have observed that the module size S2 with open field datasets outshines the other modules and suppresses the baseline model with no embedding extensions. This indicates that OS2 delivered the most robust and effective results. This graph shows the comparison. The best results goes to XPERSUM S2 model. Examples of candidates and goal outputs are displayed. Now we have our best model. Our next stage involves inference and deployment. After running the inference model, post-analysis plays a key role in guaranteeing the quality and the effectiveness of the generated summaries before they go into the real-world use. With the help of expert in Mark Noakes, from a well-crafted summary, it highlights the essential nature of using the following 7 NER type in our work. Also, to get the context of the organization in the community directory, here are some entity types that involve in the post-analysis. About 5% of our top model summaries aren't really hitting the mark. This might be because of human input error, like missing services or organizational name in the original text, or a tone that doesn't really match the formality we want. We employ custom NER model to the inference summaries, and then we group them by their entity types. The various combination NER labels can be our manual evaluation threshold. Here, we plot the top 4 significant NER threshold and rank them by the number of good summary. They are 2 NER with organization name and service, 3 NERs with organization, service, and city, another 3 NER with organization, service, and audience, and finally 4 NERs with organization, service, audience, and city. It's appearance that the 3 NER with organization, service, and city stand out by maintaining a good amount of information for recreational entity types, accompanied by well-crafted summaries in comparison to other thresholds. Examples of inference output with threshold, organization, service, and city are shown here. In the upcoming session, I will provide a code demonstration. You may access the working code by visiting my GitHub repository. First, go to Export Repository. Git clone the repository. You will see all the files here. All the experiments are stored in command script. In the script, we can see the arguments for hyperparameters, safe paths, configuration, vocabulary lists, and so on. All the extension module configuration are here, along with off-the-shelf BERT configuration and the original BERT and case model in bin format. Training data are prepared here under data folder in trim, and you'll find them here. Under expert folder, it contains all the model architecture, and it was built on top of the original BERT model. Modeling.py file for a BERT implementation is used a deep learning framework, PyTorch.
Under the class embedding, we need to convert from bird to expert by adding additional word embedding so that the word embedding for expert will be the combination of original and additional embedding. Pretraining.py contains the process of pretraining. It will take dual configuration files into the model. We got a function for loading training and test data, a function for batches, and a training loop that iterate over epoch, and finally store the data in a pickle. Let's try running the bash script. I'm using a Mat2 chip, but if you have NVIDIA chip, you may install the package to speed up. The model is reading in the configuration files and also the data, and we can see the model start training. I will stop the model now for demonstration, but it might take up to hours to run. The model checkpoints will stored under results folder along with the pickle files. For Expressum again, git clone the repo. We will use Stanford Core NLP file to convert the raw data into tokenization and sentence bleeding in binary file. This file contains all the source file. Also include the expert file from the previous phrase. And it follows the same modeling and training process. Under the results folder, there are candidates and goal summary.